Hello everyone. Today lecture continuously I'll discuss about the construction of measure space. Today lecture is understanding Caratheodry Hahn theorem. Let's recall the previous lecture. Our fundamental aim is that for arbitrary set x is given, we can construct the measure space. So sigma algebra and measurable function. If for arbitrary set x is given, we perfectly construct these guys. So in the previous lecture, we can construct the sigma algebra. We construct sigma algebra based on outer measure and the mu star measurable set. Okay, the definition of the outer measure is here, and based on the outer measure, we can define mu star measurable, and the collection of the mu star measurable set calligraphic M is indeed sigma algebra. So we can construct sigma algebra from arbitrary set X. But next task is to construct the measurable function. How to construct the measurable function? Today's lecture is focused on this here. Then, how to construct the measurable function, mu? The answer is the Caratheodry theorem. This theorem is here. Let mu be restriction mu star to mu measurable, collection of the mu measurable space here. Then these guys clearly complete measure space. This means if we consider mu, we know mu star is the outer measure. Outer measure is clearly not measurable function because x, when you choose the element x, this guy is clearly not sigma algebra but arbitrary element. Okay, so this is clearly not sigma algebra, but we construct the measure sigma algebra m star fancy m in the previous lecture. So just restrict x to the domain x to restrict the domain x to the restrict fancy m sigma algebra, this guy is here. Then this function, the theorem says this function is clearly measurable function or measure. Because these guys are measure, the triplet x fancy m mu, so mu is, we can say, restrict out the measure to fancy guys m is measure space. And if we construct the measure space using this method, defining outer measure and construct the mu star measurable set, so the collection of the mu measurable set fancy m and restriction to outer measure to m, we can say this measure space is called Caratheodry measure space, named after Constantine Caratheodry. Our claim, in order to prove this theorem, if we plan the proof, this is sketch. First condition, because these guys clearly measure, we can check these properties of measurable functions. So mu star restriction m, because the notation defined here, I use the notation mu. This guy's clearly 0, and mu E is positive. Where is E an element in these guys? But this property is clearly true. Why? Because we can define outer measure mu star empty, mu upper star empty set is 0, and all of the set element is pure positive value including 0. So because outer measures defined is here, and this just merely restrict the function the domain sigma algebra, this property is clearly satisfied. So this is clear definition of the outer measure. Definition of the outer measure. Second condition is we can check the countable additivity. Countable monotonicity. So our trouble point, this here. You can check this here by next slide. But the most important point is that this is not just a measure space. This is complete measure space. What is the complete measure space? In the previous lecture, the definition of the complete measure space is that measurable set which contains all of the measurable set. Okay, these guys contains all type of the measurable set. So by definition, we can define the definition of the complete. We can define this here. Okay. So our proof must contain not only check the measurable function, but also check these guys clearly satisfy the complete measure space. So if we check whether this measure is complete or not, we can check first these properties. Every set of outer measure 0 belongs to M. What this means? We can define M is clearly these guys. This fancy M is collection of all of the mu measurable space. This is clearly sigma algebra. But we can indeed this set M is clearly contains outer measure 0. So this means if claim is here, if E in X such that mu star E, this outer measure is 0. So some element E satisfies the value of the outer measure is 0. This is 0 set. Then here, this E contains in M, fancy M. Okay, yeah, fancy M. This is our. If we try to prove this here, we can. Our claim is here, and we can prove these guys. Okay. Then, what does it mean E contains in M? When we detailedly describe based on the definition of the mu measurable set, this means for any subset in X, these properties are satisfied. This is the definition of the mu star measurable. So our claim to check this here under the by assumption. But note that this is already satisfied. So we can check, it is sufficient to check this inequality. This inequation in the previous lecture is always satisfied in the outer measure. So we can check this only, this inequality. So for our claim, for any subset A in X, mu star A is greater than these guys. The important point to prove is check the set relation. The noticeable point is here. This is so fundamental. First condition is A intersection E is clearly contains this guy's subset of E, and A intersection of complement E is subset of A. Although this is the arbitrary set, this is always satisfied when you consider the case A and E and A subset of E and E subset of A, and A is relatively, each set relatively prime. This is the case we are consider, but this is, whenever we consider this condition is always satisfied. For example, A intersection E is here subset of E, and A intersection complement E is here. This is subset of A. When you're considering this, A intersection E is A. A is subset of E. And A complement E, and this guy is an empty set. This empty set is subset of the arbitrary set. This is okay. Whenever we consider the case, this property is clearly satisfied. We can check using the Venn diagram, or directly check the set logic, the definition of the intersection, definition of the complement. This is the raised true for arbitrary set. So by using this property, we can deduct some condition about the outer measure. First condition is here, mu, because these relations are satisfied, we can say mu A intersection E is smaller than mu star E. This is the properties of outer measure, okay? But this guy is clearly 0. And when considering the domain of the outer measure, we can deduct mu A intersection E is 0. Okay? And this is condition. And also, we can say mu star A, because this relation is satisfied, because also by monotonicity, we can say mu star A is greater than mu A intersection E complement. So we can say mu A, by using this property, mu star A is greater than these guys, and this is no problem when we add in this term plus 0. This is no problem, but 0 is here. Mu star A intersection E complement and mu star A intersection E. By this inequalities are satisfied, every out of the measure 0 set is clearly belong to M. So our proof, our lemma finish can be proved. Let's go back to the Caratheodry theorem. Our claim is this guys is complete measure space, but partly we complete this proof. This theorem proved, because this we can show that this guy's complete measure space, because these guys contains zero major zero set, okay, in the previous lemma. And when we consider remaining thing is mu is the measure, but we can check mu is always this property, the first measure condition, these guys and these guys is satisfied by, because this is because mu is the restrict to outer measure. So remaining thing is just merely to satisfy countable additivity. Note that these properties are a disjoint set comparing to outer measure. So we can, to check the countable additivity, let's construct EI is the disjoint set. Each guy's disjoint means EI, and EJ is empty for all IJ, but except from I equal to J. So to check the countable additivity, we can check mu union of EI. You just check this property, satisfied mu AI. Of course, mu is the always restriction of this here. But note that when considering the equation, we can just check this properties. Claim is, although we can check the countable additivity, we can check just this equation. The reason is because also definition of the outer measure, countable sub-additivity. Countable sub-additivity vouches this equation, this direction satisfy. Okay, so we can just check this inequality. So to check this, note that mu EI, when you're considering mu EI, because this is same as these guys, because of the restriction, like I say, this is always infinite. So when you're considering the finite, I1 to k, this guy is clearly greater than the finite value. Okay. Then we can say this is in the outer measure. Even though these guys are outer measure, we can say this is same as the sigma notation. Of course, this is finite term. Why this is satisfied? The reason is also remarked the previous proposition. Even though these guys are outer measure, because these guys disjoint, in the disjoint set, this rule is satisfied. Okay, so this is clearly satisfied. In this case, y is a. We can say a is just consider, because a is arbitrary, we can consider a is x. Then this property is already satisfied. Again, because considering the restriction, this is same as here. Okay, mu EI. And this property satisfies for all k in natural number. Because this satisfies for arbitrary natural number, we can say mu ei is greater than, this is infinite. This is also infinite. I forgot the fundamental notation, but this is clear here. So this is satisfied. Because this rule is satisfied, we can check this claim is true. We can prove the countable monotonicity, countable additivity. So because this is complete measure space and complete, and the condition of the measurable function measure is satisfied, this triplet x and mu is clearly complete measure space. So our plan is perfectly completed. Our claim is again saying for arbitrary set x given, construct, our claim is construct the measure space. This process is defining outer measure and defining mu star measurable space. This is rule to extract the sigma algebra from arbitrary set. And measurable function construct by the Caratheodry theorem, or both for Caratheodry theorem. So mu's outer measure restrict to the band CM. This guys is complete measure space. So whenever arbitrary set x is given, arbitrary set x is given, by using this process, we can always extract the measurable space, measure space. And I want to talk about the measure space, Caratheodry measure space is here. In the previous lecture, I explained the outer measure induced by set function law. So this is a good example of the outer measure. So if this, because these guys are clearly outer measure, we can say if we use this method, we can define mu star. We can define mu star this method. Clearly, we can construct the measure space. So, if the measure space is constructed by this outer measure induced by law, we can say this measurable space x and mu is say Caratheodry measure induced by set function law, because this measure space is constructed by the definition of the outer measure induced by law. Then let's change our topic. In our topic, the Caratheodry measure theorem into the Caratheodry Hahn theorem. What is this? The motivation is here. When considering the Caratheodry measure space X and sigma algebra M, it is called mu star measurable, collection of the mu star measurable, and mu. Mu is the special measure. Restrict outer measure into the mu measurable set. Okay, this is we called Caratheodry measure. But when considering this process, this is just restricting the domain X into the M, which satisfies the sigma algebra condition. So this idea implies the arbitrary set is X given, we restrict to the sigma algebra M. It is called mu measurable. This idea implies restrict X whole set X to the sigma algebra. However, in this time, I think another idea. In this case, I start from arbitrary set S, subset of S. Clearly, arbitrary subset S is clearly not, in general, it cannot be sigma algebra. But I want to construct the measure space. In this time, I want to construct the measure space by extend S to M. By extending the arbitrary set to the measure space, sigma algebra, I want to construct the measure space by extending method. This idea, in this time, I think that I want to discuss this idea. However, many others give S some condition at least. I think that maybe to easily construct the measure space from subset of S. Some others give the start from S from an algebra. What is the algebra? Algebra is sigma algebra. But if the element X is finite, then we can say this guy is an algebra. For example, if X is 1 to 3, and in the previous lecture I remarked, base 3 is given here. This is clearly algebra, sigma algebra. But this element X is finite, we can say this is algebra, just an algebra. So if we choose S by algebra, which is finite element but satisfies the sigma algebra properties, so this is algebra, we can, by this on algebra, we can extend M, the measure of a space, and finally construct X and mu can be a measure space. This is one of the idea to extend S to M. However, majority of others use the definition of an semi-ring instead of an algebra. So start from the semi-ring. Some others extend the measure space in order to construct the measure space. Then, what is the semi-ring? The definition of the semi-ring is here. An empty collection of S of subset of X is called a semi-ring if empty set in S and A intersection B in S, whatever we choose A and B. And if we calculate A set minus B, these guys express the countable finite disjoint union in S. If these conditions are satisfied, we can say the set S is semi-ring. As you know, semi-ring is more naive condition than on algebra. Algebra can be a semi-ring. However, semi-ring cannot be on algebra condition. More detailedly, when you consider sigma algebra, every sigma algebra can be on algebra. However, this is not the case because on algebra is already defined a finite element. Okay. However, in this slide, I want to introduce how to construct measurable space starting from the semi-ring. Okay. So it also requires X, M, mu. However, to construct the measure space, sigma algebra is relatively easier in this restrict case because we know we define just low s is here. What is the low s? Low s, sigma s is the smallest sigma algebra. smallest sigma algebra which contains S. Set S. So in this method, we can easily construct. Maybe we can easily construct the sigma algebra. However, the construction measurable function is relatively, I think, relatively difficult than in this restriction case. In this case, just restrict the sigma algebra. However, in this case, it's not. Our next slide is extend how to construct measurable function or measure by extending S to M. So in order to understand this process, let's see the following definition of content and free measure. Okay, we start from the array semi-ring. So let S be the semi-ring on the set X and consider mu lower star the set function. Note that this is the index is below. Mu star is outer measure. Star is located in upside. This guys is downside. Okay, so mu down star, lower star is first define content. If mu lower star is 0 and mu lower star is finitely additive. If this finite disjoint set is given, following equations are satisfied. We can say if these two properties satisfied, we can say mu lower star is content. However, in particular, if mu star lower star satisfied sigma additivity, this is discriminated as countable additivity because as we know, this is not clearly measure or measurable function. This guys is a semi-ring, and clearly this is not sigma algebra and not algebra. So in order to discriminate the countable additivity of measurable function, so you can say sigma additivity. So this is the same as we see the definition of the countable additivity. Pairwise disjoint element satisfies this equation. But this is clearly not measurable function, just semi-ring. So in the semi-ring, this property set on a content satisfies this condition. We say this property is sigma additivity condition. Caratheodry theorem. This theorem answers how to extend the measure space we desire. So let's read the theorem. Let S be a semi-ring on the set X and mu rho star S semi-ring to the real extended value is content. And suppose mu star upper star is the outer measure induced by set function mu rho star. What is the measure induced by the set function premeasure? In this case, content. When the original definition of the outer measure induced by the set function rho is here. This rho is the set function, but instead of rho, this located in mu rho star. This is clearly set function. The special name is a content. Anyway, this is a set function. And consider outer measure induced by the content. Then, following theorem is satisfied. Only outer measure induced by set function is content. Following theorem satisfies. Then this is theorem, Caratheodry theorem. The first condition, if we outer measure here, if we restrict the outer measure induced by the set function content restrict to the semi-ring, this is just content. And second property, if outer measure restrict to the collection of the new star measurable as good as the sigma algebra, is a measurable function that extends to the premeasure mu star to a sigma algebra containing row S. So let's understand Caratheodry Hahn theoretism as following diagram. We know let's consider outer measure induced by the premeasure. So this means this here. Then set function is the premeasure. Then if whatever outer measure is given, we construct the mu star measurable, and if we restrict to the mu star measurable, then we can get Caratheodry measure. Okay. And if we check this property, this means if this is true, if we outer measure restrict to the semi-ring, this equation is satisfied, then we can get automatically the second properties. Because this is satisfied, we also get out premeasure by restricting Caratheodry measure. Okay, so we can restrict mu row in S. We can get this premeasure. So following diagram, this rule satisfies, so we can say mu lower star. This means because mu is here, you can say this is here. So finally, just written here, this is same. And because this rule satisfies, we can naturally extend the free measure to the Caratheodry measure in this direction. In this case, the measure space extended to premeasure is clearly X, and the Borel set, which contains the smallest algebra, which contains the semi-ring, and outer measure restrict to M. Of course, in this case, the relation is here, S in subset of the Borel set. This is clearly the definition of the Borel set, and this subset of the mu star measurable set. So if we check this here, we naturally extend premeasure to the sigma algebra containing Borel set. So check this equation is more important task to understand this theories. In order to prove the Caratheodry Hahn theoretism, I'll explain some lemma. First, the definition. Let's see the definition of R. R is the union of AK, where each guys are disjoint. But why the definition is useful? In this definition, let's see this definition of semi-ring. Remarkable point is semi-ring. Empty set is arrays contain S, and A set minus B arrays express the disjoint union. So if we consider A set minus empty set, this is still A, but because when considering the definition of the semi-ring, this always expresses the finite disjoint union. Okay? Clearly, there exists AI, each guy is finite, A1, A2, AN is disjoint, expressed by this form. So we can say whenever we choose in any semiring, these guys contained in this R. So this means S is subset in R. Okay, we can understand this here. And of course, we can understand these properties all case of the semiring. Okay, then let's see the following lemma. Suppose mu rho star be a content, and for any A in R, in AI in R, so semiring arrays in contain the R, following properties are satisfied. I'll not prove this property, but while proving the Caratheodry theorem, I will use this lemma. And let's prove the Caratheodry theorem. I already said if we check the first equation, the second property is automatically satisfied. So our proof is to check this. We'll check this equation. To check this equation, I alternatively prove this inequality and this inequalities. Okay. Then let's check this inequation. But however, let's start from mu lower star and pick for arbitrary element in S. If we check for all element in the semiring, if we finally obtain this inequality, we can check this direction. Okay. Then, however, note that A is the semiring. Semiring is contained in R. This means A expressed by finite disjoint element of union. Originally N, however, it is no problem, infinite, when AK is empty, when K is greater than N. If A expressed the finite disjoint union, this is no problem. Okay, then we can apply the first lemma I explain. So, because this is clearly this direction imply this direction, we can say these guys greater than the summation mu lower star AI. However, if we take infimum in these guys, this is more smaller. Of course, AI, note that AI, the definition of the semiring, each members in S. So this guy in S, and A is clearly covered because of this here. Okay? Then this is the definition of the outer measure induced by premeasure content. So in this case we can write this is here. However, if we restrict to, because A live in S, if this is no problem if you restrict to A in S. So Because of this, we can check this inequality. For all AS, this inequality satisfies. And let's check this direction. Of course, this property is also valid because A is a semi-ring element. And I'll start from mu, in this case, lower star A. Note that A is expressed here, and by the second property, this guy's sigma sub additivity is satisfied. So we can write this is here. K to 1 to infinite mu lower star AI. Because this is always satisfied, this is no problem if we take infimum. Of course, in this case, still AI in subset of S, and A is covered by this here. Okay. Then this is definition of the outer measure induced by content. So this is low A. And this is no problem if you restrict to S semi-ring in A. So for every element satisfies this inequality, we can check this direction is also satisfied. Last thing I want to talk about is the uniqueness of a premeasure. In fact, when we try to extend premeasure to the Caratheodry measure, the premeasure is not unique in general. However, if premeasure is sigma finite, what is sigma finite? I'll explain the definition of the 15th lecture. Sigma finite, then the Caratheodry measure is unique measure and which extend mu rho star. So, okay. So I finished in construction of the measure, and next lecture I will explain the Lebesgue measure.